Hello everyone, my name is Alberto Ibarrondo. I am a PhD student in IDEMIA and Eurocom, and today I will be presenting you practical privacy-preserving face identification based on function hiding functional encryption, a work performed jointly with Hervé, Chabanne and Melek. So this is the agenda for the presentation. We'll kick off with an introduction, we'll then jump into the preliminaries, namely biometrics and functional encryption. We'll then dive deep into each of the elements of our solution, validating everything with our experiments, and closing up with some conclusions. I hope you enjoy it. In the introduction, we'll start with the motivation of the work, which is, as said by the name of the paper, to perform face identification. That is, to match a person's face against a database of pre-recorded faces. And we want to do this while keeping all the personal data private. When we say personal data, we don't actually mean the live and pre-recorded faces, but rather the biometric templates that arise from them, the live and the reference biometric templates. A template is in fact just a vector, a short, succinct representation of all the important key features of a face that allow you to compare faces among templates among each other. This would be applied to a scenario of a somewhat centralized identification, where on the left-hand side we would have the owner of these reference templates that would already be secured. At the bottom side, we'd have a capture device that would be getting a live template and securing it at the same time. And finally, we'd have some kind of identification system that would be performing the identification in a secure manner. Now, with this in place, we'll jump into the preliminaries. We'll talk about biometrics in a very generic sense, which is with a standard biometric system. The system would be composed of two distinct phases. First one would be the enrollment, where we're taking the reference biometric trait. In our case, this would be a face. We capture it with a sensor. We then perform the mapping towards a vector, a template, using feature extractor that is generally used in at least in the state of the art, based on deep learning. Obtaining the reference biometric template or templates, depending on the number of faces, would be storing all of them in a database alongside the identities of the people they belong to. And with this, we can close the enrollment. Then we have the online phase, that would be the matching phase, where we're once again capturing a biometric trait, this time in live. So we're capturing the face with a sensor, using the same feature extractor to obtain the live biometric templates. And once we get it, we can compare this biometric template one-on-one with a selected record, or one and with all the records of the reference template database. Similarity-wise, to see how close they are. Normally, for faces, the similarity is normally based on inner dot product of the vectors. Once we get the score, we'll be getting the highest score among them, and we will be comparing this highest score with a given threshold delta to decide if it matches this the identity or not, then rejecting it. In this entire system, we are aiming to protect the reference biometric template on the left, the live biometric template on the right, and the similarity computation in the middle. To make them private, we'll be relying on functional encryption, or more explicitly, one subfamily of functional encryption that is called inner product encryption, to perform the inner product on the similarity in a secure manner. This is performing z equals x times y, being x and y the reference and live templates, while preserving the privacy of one of them. However, the standard functional encryption or inner product encryption is not enough for us. We need to add one extra constraint, one extra condition. That is, we want to protect both x and y at the same time. For this, we need functional hiding inner product encryption, of FHIPE in short. And these are the four algorithms that compose this scheme. One by one, we have the setup that generates public parameters and master secret key MSK given a security parameter lambda. Then we have the key generation that generates functional secret keys SKY for given inputs y using the master secret key. And in fact, thanks to the function hiding, this SKY completely hide the information of the inputs y. Then we have the encryption step, where we use the master secret key to encrypt message X into the ciphertext C. And finally, we're going to be performing data encryption using the functional secret keys SKY, the ciphertext CX, and the public parameters to, in return, obtain the evaluation in plain text of set equals x times y in the dot product. With these two building blocks in mind, the biometrics on one side and the functional encryption on the other, we're going to now roll out our solution. First of all, we're going to be setting up some security goals and talk about a bit about the threat model that we're considering. In terms of goals, we already talked about a lot about the privacy that we want all the templates to preserve, but we also want to protect some other notion of practical privacy, which is protection against the leakage of the inner product itself. Well, we'll see a bit more how it works in the next slide. In fact, FHIPE already gives us privacy on the biometric templates. It does reveal the result of the inner product without the use of a decryption key. That would be unlike the case of homomorphic encryption, where you need the key management for this decryption key. And besides, it doesn't need extra communication to reveal the final result, unlike the multi-party computation equivalent. However, much like homomorphic encryption, there is no inherent protection against active adversaries, meaning that at least in our scenario, we'll be considering only honest but curious adversaries. And beyond this, the disclosed result of the inner product leaks some information about the templates, and this is generic for all secure computation techniques, which is that given the properties of the function we're computing, there is some leakage of the outputs in the of the inputs in the outputs. So what we're going to study now is how much and how to deal with it. Before going into all the details, we're going to visualize what the consequences of the inner product leakage are in our standard biometric system. So let's consider an adversary that first is able to submit as many queries as he wants to the live biometric trace, so basically submitting many faces. We're also going to consider here that the feature extractor might be known, and he might have complete control thus on the shape of the live biometric template. Then since we're not protecting the resulting score, he is going to be getting these resulting scores. And the thing is that thanks to the small leakage that he gets for each query, he can finally reach a point where he can univocally retrieve the reference biometric templates. The problem with this is that he would be able to impersonate someone from the database. A bit more in detail, this inner product leakage leads to the full reference template extraction. As we were saying, but more in detail, each evaluation of set equals x times y for a chosen x and a hidden y is going to be leaking one dimension of the k-dimensional template y. This, in short, just means that with k evaluations, we can solve a linear system of equations and we can get the exact value of the reference template y. To avoid it, we will just set a limitation on the number of evaluations of this inner dot product, n, which would be n less than the number of dimensions k. We'll enforce it in our system by adding an access control step for the live template acquisition, that is for the entry point of the adversary that we're considering. However, the adversary doesn't need the full reference template. In fact, the brute force impersonation attack would be enough to break our identification system. This would look a bit like this. The adversary would still perform n queries, and with all the information of these n queries, he would have n dimensions, the equivalent of n dimensions filled. He would fill the missing dimensions from n to k with either random values or handcrafted values, so that he could already be sending this crafted live template. And in fact, this live template just needs to match the reference template above a given threshold delta in order to perform a successful impersonation. So it doesn't need to be the exact reference template, it just needs to be close enough in an inner dot product sense. To avoid this brute force impersonation, we're going to be limiting the number of evaluations n to be less than k minus an extra threshold, an extra security margin tau, which will be equivalent to 2 to the power of 80 bits of uncertainty under the given reference template size. Now that we've dealt with the leakage, we're going to be starting on the optimization of the online phase. And that will come from the fact that we're going to be swapping the encryption with the key generation. We'll see why. In FHIP schemes, the X and Y inputs could both be set to be reference and live templates undistinguishably. And this is because their security properties are mirrored. In fact, if we see it on the algorithms of this scheme, the algorithm that makes up for the secret functional keys and the functional keys, sorry, and the algorithm for the ciphertext, they could be perfectly interchangeable because they have the same security properties thanks to their function hiding condition. In this point, previous works all used the key generation for the live template, Y, and the encryption for the reference templates. However, we noted, thanks to our preliminary experiments, that the encryption is faster than the key generation, and thus we can safely swap them to optimize the online latency, that is, the latency that happens during the matching phase. This way, we'll be using the encryption for the live template and the key generation for the reference template. Now let's put everything together and have an overview perspective of the entire system. This is the setup that we saw before. On top, we have the enrollment phase. On the bottom, the matching phase with the two modules, capture and matching module. So in the enrollment module, beyond what we did before, we'll start with the setup of the FE scheme, obtaining the public parameters and the master secret key. We will then be using this master secret key to perform key generation on each of the freshly extracted reference templates, and we will not be storing these templates themselves. We'll be storing the secret keys that result from performing this key generation, so that if this entire database was leaked, no information would be leaked by itself from these secret keys. Then we jump into the matching phase, where the master secret key is sent to the capture module, and once the live biometric template is obtained from biometric trait, we will be encrypting it with the master secret key to obtain the secure live template C, in the ciphertext C. This ciphertext, alongside the entire database of secret keys and the public parameters, will be sent to the matching module, so the matching module can perform an record-wise decryption of C with each of the secret keys, obtaining n total values. These values are already in clear text, and we will the matching module will take the plain text maximum of these values to obtain the final similarity score. The similarity score then is compared with a given threshold to decide if it's a match or a rejection. At this point, however, we're missing the one last block, which is the access control at the very beginning of the capture module, in order to hinder or completely stop the inner product leakage that we saw 2 slides before. This access control, however, we're leaving it for an open implementation that could be done either with some extra token or password access, or with an real person checking the access to the capture module. Now let's validate the experiments with some experiments this entire solution. For implementation, we used the Cypher library, and we used it based on the language called Cython. Cypher library can be found in this link. For the faces and the face identification accuracy, we're going to be using a dataset that is very well known in the face recognition domain. It's called labeled faces in the wild. We'll be also using a state-of-the-art feature extractor with templates of size k equals 128, so 120 dimensions. And at this point, we noticed that these extractors are outputting floating point values on the templates, meaning that we're going to need to convert these floating points into fixed points. At this point, we're going to have a trade-off. This trade-off arises very commonly in secure computation, also in homomorphic encryption and in secure multi-party computation. And it comes from the fact that with more decimals, we get more identification and better accuracy on our system. But however, our entire FHIP scheme is deemed slower due to it. And finally, we'll keep one question to be answered in our setup, which is how many identities can we have in the database while still having pseudo real-time matching. And when we said pseudo real-time, we almost arbitrarily set that to be up to 5 seconds. So let's jump into the results. First of all, we record the block by block latency using a single core, and we can split it into two tables. First one being non-dependent on the number of bits per template, having the setup to clock 0.35 seconds, the key generation clocking 0.19 seconds per key, and the encryption 0.082 seconds per ciphertext. Here we can already see that thanks to having swapped the key generation and encryption, the swapping reduced the latency of the live template protection, that is, the protection of the live template in the capture module, by 55%. Then, dependent on the number of bits per template element, we have the decryption that happens in the matching module. And we see that above 10 bits per template element, the decryption is taking a considerably long time, and it is unpractical for pseudo real time. And finally, just to bear in mind that the feature extractor, we chose one that was optimized for latency and thus clocks 36 milliseconds, and it's almost unnoticeable compared to the rest of the elements of the system. Now, to jump into the actual more detailed results, we have three graphs here. Let's go one by one. On the left-hand side, we have the number of reference templates on the x-axis versus the latency of the overall system of the live matching phase. And here we can see that there's this red area. There's the area where we would not be able to perform operations without leaking the entire database. From this graph, we note that we can reach up to 108 identities without fully disclosing the reference template database. Then in the middle, we can see that we have a comparison between the number of bits per template element, and in the vertical, the amount of errors that we perform in terms of identification. So the less the errors, the better. Here we know that beyond the 6 bits of template elements, there's very little to almost no improvement. So we will restrain ourselves to be up to 6 bits. Then finally, on the right-hand side, we're plotting 4, 5, and 6 bits per element with respect to the latency and the number of errors. And here we know that there are two good trade-offs. First one would be L equals 5. It would yield a higher precision, but giving us up to 70-ish identities to keep it below 5 seconds. And then we have the trade-off of having many identities, sacrificing some error rate, but in exchange reaching up to 100 identities with no problem, without a full leakage. All in all, and just to conclude, we're going to have two main takeaways. We're offering a privacy-preserving system that is based on the use of FHIP to preserve the privacy of all biometric templates, and we're dealing with the extra practical leakage of the inner product leakage with the addition of an access control step. And we're talking about a practical face identification scenario where we optimize the only latency by swapping the key generation and the encryption, and we reach up to 100 identities matched in less than 5 seconds. This was everything, and I hope you enjoyed the presentation. I'm here for any questions you may have. Thank you very much.